In lesson 17 in module 7, we're going to be talking about distance on the coordinate plane. And at first it's going to seem really easy, but then we're going to have to use one of the tricks we already know how to do to figure it out. Here's what I mean by it seems really easy. Look at example 1 here. What is the distance between the 2 points A and B on the coordinate plane? Well, don't overthink it, right? We're going over 1, 2, 3, 4, 5, 6. Okay, so they are 6 units apart. The distance between them is 6. Even if we counted this way, it's not going to be -6 because distance is always positive. Same thing over here. How far is it between B and A? Well, 1, 2 units. Not -2 units. Distance is always positive. Awesome. Super easy. Let's look at the next one. What is the distance between A and B? Can I count somehow? 1, 2, 3, 4, 5, 6. Does it work? Is that 6? No, they're not the same, right? Can I measure it? What unit it's going to be in? Unfortunately, not quite as easy as the first two. But fortunately, we can create something here. We can draw a figure on here that will allow us to find the distance between these 2 points using something we already know how to do. Ready? What happens if I draw some more lines in? I think I should have used a little bit thicker of a line. What do you notice on the coordinate plane that I am drawing? Hopefully you're telling me it's a right triangle. So if I want to find the distance or a length on a right triangle, what do I use? We can use the Pythagorean theorem to help us find distances between 2 points on the coordinate plane. And it's one of those things where you're like, oh, I don't have enough information. But if we can use the idea that we can create right triangles, they have to be right triangles on the coordinate plane, then we can figure out what, in this case, our hypotenuse is, right? Because at the longest side, it's always across from the right angle. Now, would it matter if instead I drew my triangle this way? Nope, it's really not going to matter which way I draw it, just as long as you have a right triangle. Now, the power in a coordinate plane is we can count the units, right? The distance from B to like our vertex here, right, is 1, 2. So this side is 2 units. This side is 1, 2, 3, 4, 5, 6 units. So those make up our right angle. Those are my legs. So I can say 2 squared plus 6 squared is equal to c squared. Because again, we're looking for c, our hypotenuse. That's the distance from A to B. 2 squared means 2 times 2, which is 4. 6 squared, remember, means 6 times 6. 6 to the second power is 36, and that equals c squared. 4 plus 36 is 40 equals c squared, but that doesn't mean this is 40 units, okay? Because how do we undo squaring something? We take the square root. And again, we're not concerned with any negative solutions when we say what number times itself equals 40. We get c equals the square root of 40. Now, depending on what the directions say, if we need an exact answer, we have to look at for perfect squares. So this is maybe kind of a good time to practice looking for perfect squares, right? So we have a list of perfect squares. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49, and we can keep going, okay? 1 doesn't count. 1 is a factor of every number. So if I look at my perfect squares here, which ones can we divide 40 by? And that's 4. So this would be the square root of 4 times the square root of 10. The square root of 4, what number times itself equals 4 is 2. Now 10, before we just bring it down, are there any perfect square factors other than 1 that go into 10 that can be divided by 10? No. So our exact answer is 2 times the square root of 10. our approximate answer, if I type in 2 times the square root of 10, works out to be 6.32455 ... right? So we could say it's approximately equal if it said to the nearest tenth. It doesn't really say here. That 2 tells us keep it at 3 or rounded to a 4, keep it at 3. So it's approximately equal to 6.3. Okay, so this length here is approximately equal to 6.3. Now remember, I thought, well, it's around 6, but now we know what it is. It's not 6. We have our exact answer and our approximate answer. So let's look at a couple more examples of using our Pythagorean theorem after we create a right triangle. All right, we're only going to do exercises actually 1 and 2 here, but it says determine the distance between points A and B on the coordinate plane, round your answer to the nearest tenth. So I want to know how far apart A and B are. Okay, you can't just count because it's not perfectly going through like the grid lines, right? So what we do is we create a right triangle. And it doesn't matter if you go this way or go this way, but it has to be a right triangle, meaning it has to be perpendicular, meaning you have to use the grid lines. Okay, you just can't make some random triangle anywhere. Okay, so there's my right triangle. I'm solving for my C, my hypotenuse. Okay, and then we just count the sides. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so missing side length, right triangle, Pythagorean theorem. The legs are the sides that make up a right angle. So 6 squared plus 5 squared equals C squared. 6 squared is 6 times 6, not 6 times 2. 6 times 6. 6 times 6 is 36 plus 5 times 5 is 25 equals C squared. 36 plus 25 is 61. Now it says round your answer to the nearest tenths place. So when I take the square root to undo my squaring, I get C equals the square root of 61, but it wants us to round it to the nearest decimal. So I'm going to, and again, if you don't know how to use your calculator to find these things, please come see me. So I'm going to take the square root of 61. And if it's not a perfect square, it's an irrational number, right? It keeps going forever. This is 7.81024 ... Tells us to round to the nearest, or to the tenths place. So the 8 is in the tenths place. I look at the one behind it. Does the one tell me to stay at 8 or go to 9? Stay at 8. So we're going to say that this is approximately equal to 7.8 units, whatever they are. All right, let's get one more quick example. All right, so this one is long, right? Okay. But again, you can't count. It's not going through grid lines. So we need to create our right triangle. So you just kind of go down and over so they're right at the grid lines. Because when you do that, that gives us the right angle. That gives us the C, the hypotenuse we're looking for. And then we can count, because they're vertical and horizontal lines, A and B. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, missing side length, right triangle, Pythagorean theorem. The only one that really matters where you put it in is the C here. That's what we're looking for. So I'll say A is 4. Doesn't matter if you want to say it was 13. So 4 squared plus 13 squared is equal to C squared. 4 times 4 is 16. I know that one. 13 times 13, or 13 to the second power, is 169 equals C squared. Add 169 plus 16. We get 185 equals C squared. And then we want to know what C is, so we undo the squaring by taking the square root. Same directions as before. Round your answer to the tenths place. So I'm going to type this into my calculator. And I get that C is approximately equal to 13.6014 dot dot dot. Tenths, that's a 6. I look at the 0 behind it. Does that 0 tell me to keep it as a 6 or make it a 7? Keep it as a 6. So we're going to say that this is about 13.6 units. The length of A to B is 13.6 units. Okay? So what we're doing in this lesson is we're using our knowledge of right triangles and the Pythagorean theorem to find the lengths of segments on the coordinate plane.